Dear student, in my first lecture, I had discussed about the history of the fast reactions and some of the basic concept of the fast reactions. In the second lecture, I will explain today only one method, which is the starting point of the fast reaction, that is called the kinetics of the flow methods. And although this is a very important method, and there are two types of flow system, one is continuous flow, another is the stopped flow. But I will explain today only continuous flow. Now, before going into details of that methods, I am just showing you a table so that you can understand that for different types of rate constant, which method is very suitable. Now you see that conventional method, even 1 second or less than 1 second. Now I am just talking about this flow method. Basically, flow method, if the rate constant is 10 to the power 2 to 10 to the power 8, and basically this continuous flow method, this type of reaction can be studied. But if the rate constant is beyond this 10 to the power 2, then of course stopped flow kinetic method will be used. Similarly, if you want to study a reaction whose rate constant is 10 to the power 11, like water reactions, because that is the starting point, Manfred-Eigen, so therefore relaxation method will be used. And there are two things, as I told you, one is temperature jump, another is the pressure jump. So there is sometimes it is a perturbation type of things. And in flow method, you must remember that there must be some steady state kinetics, steady state. Nuclear magnetic resonance method, we can also study this 10 to the power 11 and other things. But as you told that ultra fast technique is also in your prospectus, so femtosecond means up to 11 is then if we need the 10 to the power 15, then of course we have to use the femtosecond spectroscopy. So next time I will discuss this femtosecond. So I will concentrate only today is on flow method and continuous flow method. So again I am just showing you the fundamental first point. Now again, if it is a flow method, so suppose this is two, I will show you the first structure. So we need some plunger, so A and B. Then we need some reaction mixing area, mixing. Then if it is a continuous flow, so there must be some detector, any type of, I am talking about the detector, which can detect the color changes or absorbance or whatever it is. This is movable because that is moving these things. But if it is and then of course a drain is also required. But if it is a stopped flow, so there must be some device by which you can stop that flow. Okay. So that is the difference between the continuous flow and the stop flow. Now in continuous flow also, the first method is called the plug flow. P-L-U-G. Don't confuse. Plug flow. Plug flow means plug flow. That means we need a reactor and we monitor, suppose there is a particular volume element. So we have to determine that flow, the movement of that flow, volume element with respect to time. That is called the plug flow method. I'll explain this plug flow method. Now, I have already told you these things. Yeah, our objective is that quickly mix the reactants and then observe their spectroscopic change. Suppose you have a spectrophotometer. So what you will do? You will monitor the absorbance of that mixture after reaching the equilibrium. Suppose you have a spectrophotometer. So you will monitor the fluorescence with respect to time. Suppose you have a NMR machine. So system is same, two plunger and that you are forced monitor the chemical shift like that. Suppose you have a conductometer. So you will measure the conductance of that mixture. You have a potentiometer. You measure the EMF of this thing. So there are two parts. One is device for mixing, and then there is a chamber, mixing chamber, and another is the detector. That is the fundamental points. So I am just coming to this diagram. One is, this is a very common example, can be studied with the help of the stop flow method. The study this reaction instrument is required that allows the investigator to rapidly mix the reactants or part of the system in a controlled way. And second is the monitor the concentration. Monitor the concentration. That's all. Monitor the concentration. Now, there are many reactions which have been studied by the continuous flow method, but basically they studied NO and oxygen reactions. There are some salient features of that method. The continuous method is very simple. The reactants are supplied at a constant rate into a reactor, and at constant flow velocity, positions in the tube correspond to the specific times. And just we monitor this volume element, this change of flow with respect to time, we can calculate the rate constant by a very simple technique. I am just showing you the photographs. It is a sometimes when you see the instrument, there is a difference. So it is sometimes it is called the schematic diagram for understanding the subject. If you see the instrument, it looks like different. So it is just a system in everywhere. Stop flow, flash photolysis, everywhere. You need two reactants. Sometimes, suppose there are three reactants, A plus B plus C. So maybe reaction vessel maybe number 3, but everywhere you need a mixing chamber, everywhere you need a detector to monitor that spectroscopic properties or any type of physical properties. And then of course, now but if it is a continuous flow, so we have to monitor this part. So this is the difference between there are so many excellent diagrams are available in this system. Now I am just showing you the difference between the continuous flow and the stopped flow difference. Now if it is the system is again same, solution 1, solution 2, same thing. Again there is a mixing chamber and that is a detector, maybe a spectrophotometer like that. Only difference is that it is a stop flow, so we must have a device which can stop that reactions, and then we need computer and trigger and switch and other things. So that is called the stop flow device. But again you see the fundamental is very simple. Now lastly, because I have to go to a meeting just to give a time, so today I will not derive it, just to tell you. Now this is the very nice diagram of plug flow method. Now see, just you consider, this is sometimes they call a vessel or a reactor. So there are two parts. One is suppose you are taking some reactants whose concentration is C, just like a normal system, concentration of C, and you are monitoring that dV is the volume element, and this reaction mixture with the help of some device is passed through this vessel. So just like a normal system, suppose the rate constant is K, but what is the difference here? Here is that we have to calculate this volume element, the change in volume element with respect to time, and there must be a flow of that particular reaction mixture, and suppose that rate of flow of that volume element is suppose U, that is U, rate of flow of that volume, that is U. And in normal case what we do, rate is directly proportional to the concentration, you know, so, and there must be some constant, same thing just like your first order. This is C concentration, and suppose the order of reaction is N. N may be 1, N may be 2, N may be 3. Suppose first case we are talking about the N. So simply rate is K concentration, but here we are talking about the volume element. So therefore we have to write rate is equal to K C N and then volume element with respect to time, suppose. So this is one part. Second part is that when these molecules of the reactant enter the reactor with this particular rate, so we can write this is UC, C is the concentration, and of course with respect to time. When this cross these reactors, there is a change in concentration, very small changes, very small changes. So what do we write? When this molecule of the reactant entered this reaction vessel, it is UC dt. But when it crossed that volume element, there is a small changes, and it should be U, suppose change C plus DC, small changes. and then of course dt. And when that system reached in a steady state, so what should I write? I should write u c dt, first point, equal to u c dt before this volume element. So the u c dt. There is a steady state equilibrium. It is equal to u c plus dc, u c plus dc dt plus k c n dv dt. And from that equation, you just, if you equate this equation, you can calculate the rate constant. How do I equate these things? I can write like that: u c dt is equal to u c dt plus u dc dt is equal to this. So this u c dt can be cancelled out like that. So by that method we can calculate this k. I was talking about the plug flow method. So this is actually volume element, as I have already discussed. Volume element, and concentration of that reactant is N, and the rate of flow of this volume element is U. I have already told you. Now there are two conditions. Number one is the number of moles of the reactant enter. Very simple derivation. So that is U C concentration dt. So this is entering in the solution. And this flow movement, so number of moles of the reactant leave, LEAVE, that is U C plus DC at with respect to time. So one is actually number of moles of the reactant enter. There is a change in volume element, and number of moles of the reactant leave in this section. This is one condition. Now, if I want to calculate the rate constant, so K rate is equal to C N, normal case. But because we are concerned about this flow of this volume, so rate of conversion with respect to volume, so it is, therefore I have written dV. That is disappearing, that reactant is disappearing, and normally now so what is the condition? After attaining the steady state, number of moles of the reactant entered UC dt is equal to, one is disappearing, another is also leave. So u c plus dc dt plus kcn, order of reaction, dv dt. Just we solve it. uc dt is equal to uc dt plus u dc dt plus kcn dv dt. So what I can write? What I can write, if I just rearrange this equation, minus u, rate of change in volume, u dc dt is equal to kc n dv dt. Again, so I can write minus u dc. I'm just solving this thing, k c n dv. So rearranging these things, because it is concentration, it is rate of change of volume. So what I am doing, minus dc concentration and cn, just rearrange this, is equal to k divided by u and dv. Just your normal, for any normal kinetics, what do we do in order to know the change in concentration, whether it is a flow method? So we have to just integrate it from initial, as you know, concentration of initial to concentration of final. Here is volume to 0, V0. Now there are two conditions. It is just like a dx by x, log x, dx and x. First condition is that n is equal to 1, first order. And second condition, n is not equal to unity. Because it is not necessary that always your reaction is first order, it may be other. So there are two conditions. First is n is equal to 1. So it is just like a dx by x, log of x, of course minus is there. So what I will write? Minus, yes, natural log of C of final divided by C of initial, right, is equal to K U and dV V0. So it is actually V0. Just like you remember your first order kinetics. What I can do, I can write like that, natural log CF CI is equal to minus K by U V0. So therefore C of F, just like your A is is equal to A0, like that. C of I exponential minus K and V0 divided by U, rate of change in volume. Just you see, just like your first order kinetics. So now, of course, there is a term, this V0 volume element and rate of change of volume. You can write T. That is called the contact time. Contact time. Therefore, this equation can be modified as Cf is equal to Ci exponential minus K, whatever the rate constant. It is, you can write like that. You follow my point. It is just like your first order kinetics. A initial A0 exponential minus KT. So that means in first kinetics only we modified the system. We modified the device. So lastly, for if n is not unity, suppose, so your reaction will be 1 n minus 1 bracket 1 divided by C f n minus 1 minus 1 Ci n minus 1 is equal to K V0 divided by U. So there are two formula. One is for n is equal to 1, and second is that when n is not unity, this is the same. So here is important is that the movement of that volume element. So this is the first method. Therefore, it is important because flow method using a reactor. So it is a schematic diagram. It is if you see the original instrument, so this is just like a vessel that is called the reactor. So there is a flow of that reactor. But the negative point is that this is the first device, and large amount of chemicals are required, and we are not getting very accurate rate constants. So therefore, another Professor B. Chance, they modified the system with the same concept and developed the stopped flow method. And nowadays, most of the universities are having that stopped flow technique. And stopped flow technique is exactly similar to the flow method. Only thing is that whatever the change in physical properties or spectroscopic properties, we have to monitor with the help of spectroscopic technique. So therefore, it is called the hyphenated technique. There are two devices. One device where you will keep your reactants. With the help of some automated system, both the reactants are forced to enter that instrument, and that instrument directly monitor the change in absorbance or fluorescence with respect to time. By that method, we can calculate the rate constant for very fast reaction. In my next class, I will discuss very briefly the instrumentation of stop flow technique and relaxation technique. Thank you very much.